Hello everybody. Today I will be giving you a tutorial on how to use SaliLab's modeler to take a protein sequence with no crystal structure and compare it to a known crystal structure, and using Python we will create a suggested crystal structure for your unknown sequence. First, you'll want to navigate to the Anaconda website and download Anaconda Individual Edition. After you download this, you'll want to open the Anaconda Navigator. It will take a few seconds to open. Once the Navigator is opened, you can launch the Qt console. It will open as a small window. And in this first line, you'll type conda space install space -c space SaliLab space modeler. I've already installed this, so it will go a little bit quicker and will only output a few lines that say that it's already installed. Whenever you do this for the first time, it will give you about a page or two in this small window, and you'll know that it has successfully installed. Once it installs, you can close out the window, and then you will want to navigate to the modeler folder inside your Anaconda folder that you just created on your computer. And so I have mine installed in the default Windows pathway. So that would be in your operating system's hard drive, users, your username for your computer, Anaconda 3, library, modeler, modlib, modeler again, and then you want to look for this file called config.py. When you first open it, this right here will be 4 X's. The way that you get the license code is you navigate to the registration website on the modeler website. You can input all of your information and they will send you a code to put into this license line here. I have found that model IRANJE has been the code that I have received and that my lab mates have also received. So if you type that into the second line, file save. Next, we will go back to FPBase and grab our protein sequence. We'll take this protein sequence and head over to SwissModel to find a protein sequence that is most similar to ours. So you'll click Start Modeling and paste the sequence here, and then you'll click Search for Templates. The search should take about 1 or 2 minutes, and I've already completed the search for this protein. You will then be pulled into this page where they will show proteins with similar structures that they recommend to you. So you want to look for a protein that has either the exact same or a very similar chromophore to yours. So I know that AGFP's chromophore is SYG here, and then in the protein that it gave me, 1QYO, the chromophore is this GGG here, and so we will try to model against this protein. Once we have the known crystal structure, we will want to navigate to this RCSB link. This will open the protein database link for this protein, and we'll want to download files, the FASTA sequence, and also the PDB format, and that should download these 2 files. You will then want to go into your desktop and create a new folder, and you can leave it titled as new folder, and we'll want to move these newly downloaded files into this new folder. So if we open it, then we can grab the files and move this 1QYO.pdb into the new folder, and also this FASTA file into the new folder. When we move the FASTA file over, we'll want to take away the RCSB_PDB_. So we can just go in here and rename this and leave it as 1QYO.FASTA. I don't know how much it matters, but typically I like to capitalize these, 1QYO. There's another file that you'll need to add to this folder on the from the modeler website. If you navigate to the modeler website and click on Download and Installation, there will be a link down here that says Supplemental Data File Downloads. This PDB_95.pir is in a zip file, which is indicated by the .gz. If your computer has a way to open the zip file, then you can just download it from here and then grab the file. I already have the file downloaded and moved to my desktop, so I will just place it in the new folder that we created here. In this new folder, we will then want to create a new text document, and this text document will be renamed to our protein's name. So in this case, it's AGFP, and we want to make this a .ali file. And then yes, we want to change the file extension. If you have not changed your settings on Windows, you should go into the folder and click View and then File Name Extensions. That will allow you to change the type of file. Then we want to open up this notepad, and you will want to copy what I paste in here. Anywhere that has your protein name, we want to change it to AGFP or whatever your protein name is. So I will do that here, AGFP. And then we want to grab the protein sequence again. So we go navigate to FPBase, and we grab this sequence for our protein and paste it right here. It's important that there's an asterisk at the end of your protein sequence, and then you can hit File and Save and exit. This next part, I'll be creating 3 new files into this folder. For people inside of the Dodani lab, these files will be located in our box folder, but for people that are not in our lab, you'll need to follow these next instructions. So you'll want to create a new text document and call it build_profile.txt, or we'll change the .txt in a second. We want to open this, and I will move this code over. And then anywhere in here that has brackets, we want to change the brackets to whatever it requests. So this is our protein, so this would be AGFP.ali. And there are no more brackets in this file, so we'll do File, Save As, and then we want to make sure that it does not save as a text document, but rather a .py document. So buildprofile.py, and then save. And you want to check the folder because sometimes it won't save as a py, it will save still as a .txt, and in that case you just need to view the file extensions. We can delete the buildprofile.txt and double check that buildprofile.py is correct. Next, we want to create another text document. This one is going to be titled align2d.py, and then we can remove the .txt if we have file extensions seen, or as we save the file, we can also save it as a .py file. Then inside of this notepad, we want to copy this code. And again, we will change any of the brackets to the information that is requested. And in this case, it wants the PDB ID of the crystal structure. So we should pull up our PDB ID and 1QYO. So we go back into the notepad and change the PDB ID to 1QYO, and then model segment. On this PDB ID, the align codes, if the protein is not a monomer, you will need to include an A here. So I will include the A just to show you guys. 1QYOA. And then we need the pdbid.pdb file. This links to that PDB file that we downloaded earlier, 1QYO, and it does not need the A since it is linking to that PDB file that does not have the A in the title. Then this is the file for your protein that you created. So this would be agfp.ali, and then aligned codes with the protein agfp. Then it is going to create a new file that is going to be called agfp-1qyo.ali, and then we want to copy and paste this again for this one right here. This is going to create new files inside of this folder that we will see later. Again, we will do File and Save and double check to make sure all the brackets are replaced, and then exit. We have one more file to create inside this new folder. So we do a new text document. The last one is titled model-ligand.py, and we again remove the .txt. we change the file type and we open it. Then there is this last bit of code that we can paste in here. And now we can change this back to the same name from the last file. So it would be agfp-1qyo.ali. The knowns in this situation is the 1qyo. This is the known crystal structure, and you do need to include the A. So 1qyo-a. And then the sequence that we are checking against will be the protein sequence that you made in the .ali file. So it will be the agfp sequence. We can then hit File and Save and exit. In the next step, we want to move our new folder into the Spyder file on our computer so that it can be read. So we'll exit out of the new folder and we will navigate. We can go from this modeler folder back to the main PC, and in our operating system, again, under Users, Owner, and then Spyder-py3, we can move our new folder into this .spyder file. This will make it so that Spyder, the program, can read all of the files inside this new folder. And I'll again open the folder so that we can use it. Next, we should open Spyder. And we can take the files in our new folder, and the order doesn't matter, but I like to put them in the order that I run the files. So first we'll move build profile over, and then we can move align over, and then we can move model ligand over. And then in this screen, we can double check the code to make sure that any brackets are removed and replaced with the necessary information. And anybody not in the Dodani lab can again check their code against my code here to make sure that they have the correct information. At this point, I would like to take a second to note that for your proteins.ali file that we created in the new folder, so in our case, agfp.ali, if there are spaces in the sequence that you copy over, so for example, if I copy over only the first 15 residues, or the first however many residues, and paste them into this file, there are spaces. Python doesn't like these spaces, so you need to remove them from the sequence, and then after you remove all the spaces from the entire sequence, it will look like this. Having code on different lines doesn't matter because Python will just wrap to the next line if it's reading through it, but spaces count as a character that Python does not recognize. So you'll want to make sure to remove all the spaces from your .ali profile, or you will get an error whenever you try the next step. So next, we will want to go back into Spyder, and we can start running these files. So if we run build profile first, we wait till we get the green input line to show back up, and we'll notice that in our new folder, if it was successful, we have a new build profile.prf and build profile.ali. These are not important for right now. Next, we want to run the align code. So we can hit run. And then once it's finished, you will have another input, and you'll notice that in our new folder, we have a new file called agfp-1qyo. And this is the file that we want to open. Open this newly created .ali file and locate the chromophore of both the crystal structure and your protein sequence. You'll need to replace them with 3 periods. And you'll also need to increase the number of residues in the sequence by 3. Then we'll save and exit, and we can run model ligand in Python. In the folder, we'll notice that it is generating these new .pdb files, and it will generate 5 of them. And these are the files that we will move over into PyMol. And there's number 5. The program is finished running, and we will continue. Next, we'll want to open PyMol, which models protein structures. And then we want to grab all of these new PDB files and move them into PyMol. We also want to fetch our original protein, which was the 1QYO. And then we can turn off some of these to decrease the clutter. And then we'll want to type super 1QYO, comma, and then a name from over here. So AGFP B999900001. I will copy this because whenever we super the other ones, it will be easier. So we press enter. And I forgot to include the dot after GFP. So GFP dot B999900001. And it will put these on top of each other. And I can remove the waters from the 1GYO to make it cleaner. So next, we want to compare how this structure aligns with the original crystal structure. This one lines up pretty well. A lot of the disordered regions look the same, but you want to go through each of them and check the alignment to, oh, I should copy with the period in it. And we want to align this 1QYO to all of the structures, and then we'll determine which one is the most similar. So this one looks very aligned, very similar. A lot of the disordered regions look the same. Then we want to test it with 3. And we change this value to 3. This one looks very similar. Most of the disordered regions are superimposed on top of each other. And an important note is that if we open up Spider, where we ran the model ligand code, we can see the 5 files with values attributed to them. What I found is that the lower the value, the more similar that the suggested structure is to the original crystal structure. So in this case, AGFP number 3 has the lowest score, and it is the most lined up. That is all that I will be showing you guys today in this video. I hope that my tutorial was helpful and taught you guys how to model your protein sequence against known crystal structures. And I hope you have a fantastic day. Thank you so much for watching my video.